Okay, the title of this is Use of Thermal Analysis Test Techniques to Support Material Failure Investigations for Space Shuttle and International Space Station. And you see there on this second slide is kind of a brief, I've worked at the NASA Marshall Space Flight Center in Huntsville, Alabama in the United States for about 31.5 years. I don't know how many of you have been to the United States. The state of Alabama is located in the southeastern part of the United States. The bottom part of the state of Alabama kind of touches the Gulf of Mexico, which leads to the Atlantic Ocean. So it's located in that part of the United States. And I have worked at that facility for that long. My background in education is that I have undergraduate and master's degrees in chemical engineering from Auburn University, which is also in the state of Alabama, in the city of Auburn. And I also have a second master's degree in material science and engineering from the University of Florida, which is in the city of Gainesville, Florida, in the state of Florida. I work in a branch at NASA that specializes primarily in testing and evaluation of non-metallic materials, especially polymeric materials. I think I understand that maybe quite a few of you are interested or work in metallurgy, but I really don't do much work at all in metallurgy. Almost my entire career has been with non-metallic materials and even more specifically, mostly with polymers. I guess if you wanted to really condense what I do at NASA into 3 categories, it would be in material selection. In other words, maybe helping a project to select the proper non-metallic material for a certain spaceflight application. Another category would be material compatibility, understanding how non-metallic materials function in certain environments, whether they're liquid or gas, or maybe other things like radiation or ozone or things like that that can have some effect on materials. And then also the last category would be material failure investigation, where I sometimes get asked to do testing or support to try to help solve problems and determine why a certain material part maybe didn't function the way it was supposed to function and something went wrong. And so the testing would be used to try to help see if we could solve that problem.
Mr. Wingard, thank you so much. We cannot thank you enough, actually, for sparing the time and giving this talk to our students. It was certainly most useful, and it also supports what I continually tell our students. Material characterization is so important in your career. I keep saying that, and for this reason, we have 3 consecutive lecture series, courses actually, on material characterization. So material characterization 1, 2, and 3. This is a unique thing in our curriculum compared to other departments. And many lecturers attend these classes. Everybody talks about their particular field of expertise. And your DMA, by the way, works in a very similar way to our resonance frequency damping analyzer. This is also a mechanical spectroscopy system. We measure Poisson's ratio or Young modulus of materials. And your examples were really priceless for us. I also have a question out of curiosity. Now, you are working on material selection for conditions that I'm just speaking with gut feeling, and I dare to say that you are selecting material for conditions that we don't always know 100%, do we? Or maybe I'm mistaken at this point. So when you are selecting materials, how do you come up with the technical specifications for that material? Or is it a process through which the technical specifications evolve as you work on the problems before you take a material and put it into the spacecraft? I don't know if I made myself clear. Like, how does this setting the standards for materials process work? Technical specifications.
Yeah, actually, I don't work in research at NASA. I work really more in applications. So a lot of the materials that I help select are probably already commercially available materials, but yeah, we have to, quite often we're having to satisfy things like I mentioned, maybe incompatibility with certain environments, whether they're liquids or gases. Maybe also we're looking at the ability to handle maybe stress in a certain component. We're also looking at ability to handle certain extremes in temperature. As you know, though, polymers you cannot take to as high temperatures as metals, and so you have to be more careful in choosing polymeric materials because majority of them you cannot really take more than above about 300 Celsius, most of them, and so and some even less than that. So I usually look at at properties like tensile strength, compressive strength. Also, another thing, if the part is under stress, polymers will undergo sometimes they will undergo stress cracking. They can crack in certain environments, which also could be caused by compatibility issues, maybe. But things like that, certain strength properties, temperature requirements, compatibility with gases or liquids, things of that nature are typically what I look at.
I will continue with other questions. Some of the students already prepared for you. Because along with the technical questions, they are also quite wondering about your, let's say, career. That's the reason they wanted to ask you a few questions about your professional life, if you would like to answer, of course.
Okay.
The first thing that they wonder, as you already mentioned that, your bachelor degree in chemical engineering and the master degree in material science. So in principle, you have a wide range of spectrum in terms of, let's say, the research field.
Mm-hmm.
They wonder that, what drives you to concentrate on, especially on polymers in your professional life?
I don't know. That's a good question. My second, you remember when I showed one of the slides, the second master's degree I got was in material science and engineering. And really, I actually got that second master's degree right before I was hired by NASA. And so that second master's degree that I did at the University of Florida was really mainly in polymers, and it had to do with the curing behavior of a particular epoxy resin system that's sometimes used on aerospace applications. And so the fact that I did that master's degree, that second master's degree in polymers, made me have some interest in wanting to pursue a job that that is pertaining somewhat to polymer science. And so luckily I was able to get that kind of job offer from NASA and end up working in that area. And it just so happens that I have spent really most of my career working with polymeric materials or non-metallics, and have really done not very often with metallic materials. I showed one example today looking at this lithium aluminum alloy, but an instrument like a DSC is really not as conducive to metals unless you can look at something like an aluminum alloy that has some lower temperature transitions that show up in the neighborhood of maybe the 200 to 400 degrees C range. You remember me telling you that you really don't want to take your DSC above about 600 degrees C because of the aluminum sample pans. And so it really is not that favorable for metallic samples. So it really is more used for polymeric samples, and also the DMA, because of the amount of strain that you put on your sample is very small in a DMA. The amount of strain in a dynamic mechanical analyzer is usually only in the micron range, whereas on a tensile machine like an Instron, where you're pulling a sample to failure, you're actually putting quite a bit of strain on your sample. And so the fact that the DMA uses very, very small strains, it's also not really conducive to metallic specimens either. So I've used those techniques like DSC and DMA primarily for polymeric samples or non-metallic samples, and so I really have spent majority of my career in polymers.
I mean, since you are, the material engineer in such an organization, the NASA.
Yeah.
The first thing that they wonder, how does the working in the NASA make you feel, and what kind of, the advice, suggestions could you give them to, in order to, let's say, achieve such a successful career? They are wondering this type of information from your side.
Yeah, I guess I have been very lucky to work for NASA because it is at least in the United States, it's a pretty high visibility organization. Unfortunately, a lot of times when people learn something about NASA is when something goes wrong. When something bad happens, like these accidents we had that killed the astronauts. Of course, those are terrible tragedies, but since I work there, we have to deal with those kind of things, and so we had to investigate those kind of accidents and see what we could do by testing to help solve some of those things. I guess if I had to make any recommendations to students, is that even after 31 years, you don't stop learning about subjects just because of college. Once you get out and start working, you still have to study subjects, right? And so I'm still, anytime I'm involved with these kind of projects, I still have to read and study about properties of materials, and so I still have to do my own research, almost as if I was studying for an exam, So it's so once you're out and start working on the job, it's you never stop learning. You still have to motivate yourself to keep learning.